So thank you very much for having me. Today what I'm going to do is talk about how a few different strands in things I've been working on over the last couple of years fit together, and kind of a general picture that I think kind of arises from some analysis of particular details at the foundations of the mathematical foundations of quantum field theory. And these mathematical details are important for understanding the project of going about interpreting the theory, where what I mean by an interpretation is an approach to taking the mathematical structures that we take to be constitutive of the theory and associating physical meaning, claims about the physical world, with that mathematical structure of the theory. So what I want to note is that standard accounts of how to go about interpreting a theory agree on what kind of mathematical structure is required to go about interpreting the theory. Those standard accounts are pretty well regimented about this. And one aspect that I think most standard accounts agree on, or what makes standard accounts standard, is that they adopt something that I'm going to call the exactness requirement, which is that it must be possible to determine the empirical content of a theory exactly, at least in principle. So this requirement captures the basic intuition that a theory should determine the fact of the matter about its observables. And once we have the theoretical content from the theory for an observable, then we can ask whether or not the theoretical content of the theory matches the values of those observables in the actual world. And we count the theory as saying something true about the world on standard accounts of interpretation when the theoretically determined value of the observable matches the experimentally determined value of the observable within the standard measurement error that is accrued when we measure the quantity in question. So now, what I want to point out in this talk is that, in fact, there's a serious question about whether or not this exactness requirement is in fact satisfied in the case of quantum field theory. So let me give you kind of overview of why you might think that there's reasons to doubt this kind of claim. So on the one hand, if you look at the top part of the timeline here, the history of quantum field theory is kind of marked by a large number of both theoretical and empirical successes. If you count up the number of Nobel Prizes accrued along throughout the development of this quantum field theory and the standard model of particle physics, you get to about 15. So there's no doubt that what we have is an empirically successful theory. By many metrics, it's the most empirically successful theory we've ever had. But unlike some other empirically successful theories, for example, non-relativistic quantum mechanics and special relativity, which are the basic ingredients that we feed in to develop quantum field theory, the history of the development of quantum field theory has another kind of side to the story, and it's a side that has been focused on trying to understand a collection of mathematical problems at the foundations of the theory. So relatively early in its development, people realized that quantum field theory contains three classes of divergences, or infinities, which crop up when you try to evaluate the theoretical characterization of the observables in the theory. And since those observables in many instances are probabilities, the fact that what you're getting is infinity is an indication that something has gone wrong and that we're not getting a characterization of the empirical content, which is going to be directly, which is going to tell us something true about what the observables say in the world. So in response to the presence of these three classes of divergences, which I'm going to tell you more about later in the talk, a small subset of mathematical physicists, in this case, kind of split off from the mainstream of practicing particle physicists and tried to develop kind of axiomatic characterizations of the content of the theory. And one of the central aims of this approach was to rule out these infinity problems, these divergence problems, from the characterization of the observables from the beginning by treating the problem in a mathematically rigorous way. So this project achieved some success in the sense that there are now models, there are constructive models of these axioms, sets of axioms available. But the problem for this approach is that the empirically interesting models, the models that achieved all of the empirical successes noted in the top part of the timeline, can't be shown to satisfy the axioms in question. So there's an open problem. If you want to win $1 million, all you have to do is show that there exists some collection of axioms, like the collections of axioms that we have, with respect to which the empirically adequate models, such as quantum electrodynamics and quantum chromodynamics, are in fact exact. They satisfy this exactness requirement. Okay. So this is Irving Siegel, a practitioner of axiomatic field theory, writing in 1959. He says, just what is a field theory is a difficult question, since at present what we have after 30 years of intensive effort is a collection of partially heuristic technical developments in search of a theory, but it's a natural one to examine axiomatically. And I think this kind of reflects, this has led, this kind of attitude about the mathematical characterization of the content of the theory has led to a kind of divide in the literature. So on the one hand, there is perturbative quantum field theory, which is used by practicing particle physicists, and it is empirically successful, but it contains these ultraviolet, infrared, and large order divergences. And as a result of containing these divergences, the models do not meet the exactness requirement. On the other hand, there's axiomatic quantum field theory, which is used by has been developed by mathematical physicists and has been the locus of attention of philosophers interested in quantum field theory, for the most part. In this case, the challenge is that there's no empirically adequate models. The models that we have are defined in reduced space-time dimensions, so in 2 rather than the 4 space-time dimensions of the actual world, or they don't contain interaction, so particles can pass through one another without influencing each other in any way. But the reason that philosophers have been interested in this kind of approach to characterizing the theory, I think, is that the models do in fact satisfy the exactness requirement. And so we know how to tell our kind of standard philosophical story about how physical meaning accrues to the mathematical structures characteristic of the theory. So a wild Laura appears. And I think this is reflected in the philosophical attention to the theory. And Laura says, a collection of partially heuristic technical developments isn't readily attributed to a set of models, which is a reference to Siegel in the first part. But then I think by saying it isn't readily attributed to a set of models, I take this to be part a symptom of the fact that the perturbative characterization of the theory doesn't satisfy the exactness requirement. But she goes on to note that it is in itself a philosophically provocative circumstance that such a collection can enjoy stunning empirical success. Hans Halvorsen puts the point even more forcefully, and he says that in the absence of some sort of mathematically intelligible description of QFT, and if the exactness requirement isn't satisfied, it's supposed to be in doubt whether we have a mathematically intelligible description of QFT. The philosopher of physics has 2 options: either find a new way to understand the task of interpretation, or remain silent about the interpretation of quantum field theory. So suppose what we want to do is provide an interpretation of the empirically adequate models of the theory, the models that we think actually are giving us information about the actual world. Then we have what I think are basically 2 options. The first option is to wait and hope for a new formulation of quantum field theory and use standard philosophical approaches to interpretation with because according to this new formulation, the exactness requirement presumably will be satisfied. And so we can use standard interpretation. The second option is to develop a new approach to interpretation that can cope with the presence of divergences. And what I'm going to do is pursue the second option here. And it's not just a feature of, or it's not just a result of the fact that I'm impatient and I want to interpret the empirically adequate models now. It's that I think that there are principled reasons that you might think that, in fact, divergences are telling us something important about how we should go about interpreting the theory, and that they might be an indication that there are some preconceptions in standard accounts of interpretation that aren't going to be able to cope with the empirically adequate models. And in particular, the idea that I want to develop here is that the presence of divergences is in fact a hint about how mathematical structure underwrites physical meaning. Their presence is telling us something about how the mathematics of the theory is connected to the physical content. And in particular, I think that their presence is an indication that empirical content is insensitive to exact mathematical structure specification. So what I'm going to advocate is that all of these divergence difficulties that we encounter can be construed as telling us that rather than adopting this exactness requirement, we should actually think that what we should expect from a theory is to give us a characterization of the theoretical content, a theoretical characterization of the empirical content only up to some finite level of theoretical error. So I'm going to defend two claims. The first claim is that all three classes of divergences that are present in quantum field theory can be overcome by letting empirical content have finite precision. So if you're willing to make this switch, if you're willing to allow a small amount of theoretical error associated with the content of the theory, then we can overcome these divergence difficulties. But the second claim I'm going to defend is that in order to interpret the empirically adequate models, we in fact need to abandon the exactness requirement. It's not just that we can. It's not just we can make this move. We're in fact left with no option to do this if we want to treat the models that actually make contact with the world. Okay. So the way I'm going to proceed is I'm going to systematically work through the three classes of divergences that plague the theory in the short distance, the ultraviolet, the long distance, the infrared, and then I'll explain more of what's meant by large order in a moment, and then I'll offer some brief conclusions. So let's look at the first class of divergences in quantum field theory, the ultraviolet or short distance divergences. So free fields, the kinds of fields that we can treat with axiomatic field theory, can in fact be treated exactly. We know how to give an exact characterization of them, but to describe the realistic models, the empirically adequate models, it's necessary to include interactions. And to see the effect of interactions, we can scatter particles off of one another and just see what comes out. So when we do this, the way that we characterize this kind of scattering in the formalism of the theory is we take a particular collection of incoming particles and we calculate something called the S matrix, which tells us the probabilities for finding a particular collection of final states. The idea, and where perturbative field theory kind of departs from the exact characterization of axiomatic field theory, is to treat the interaction as a small perturbation of the well-defined free fields. And when we do this, what we get as an expression for the S matrix is an infinite sum of terms where each individual term is a number, and I'll tell you where the numbers come from in a moment, multiplied by powers of the coupling constant alpha, which tells you the strength of the interaction in the theory. So early terms in that expression can be summed up to give an approximation to the value of the S matrix. And then we can compare the resulting probabilities for scattering experiments to scattering experiments that we actually can perform and get empirical values for. So suppose we try to perturbatively evaluate the S matrix in this way for a simple scattering process. The scattering process we're going to think about here is just an electron and a positron, which travel towards one another, eventually collide and annihilate to create a photon, and then later that photon moves along and then decays to an electron and a positron again. We have a diagrammatic way to represent this, given on the right-hand side of the slide. And those diagrams, that diagrammatic representation, is just a shorthand for the integrals determining the numbers in the perturbative expansion. So when you see a given diagram, that just corresponds to an integral, and that integral is telling you one of the numbers in this perturbative expansion. So because we're dealing with a quantum mechanical theory, it turns out that there's in fact more than one way that you can start out with an electron and a positron at the beginning of a scattering experiment and end up with an electron and a positron at the end of a scattering experiment. And the theory tells us that in order to calculate the probability of getting that particular final state, given the initial state that we put in, we need to sum up all of the infinite possible ways that this process can unfold according to the rules of the theory. And when we do this, when we write down all of the possible ways that this can happen, what we see is that already at the second kind of way that this can happen, we have this internal closed loop. And this internal closed loop is going to be the source of the first problem with the theory. The reason that it's a problem is that this internal closed loop corresponds to a momentum that can get arbitrarily large, and the integral corresponding to this diagram goes like 1 over p integrated from 0 to infinity, which goes like the log of infinity, which of course is infinity. But now remember, where this diagram and the corresponding integral comes up is in an infinite sum of terms, which all taken together are supposed to tell us a probability of what comes out of the scattering experiment. So it's telling us that the theory is predicting an infinite probability for getting out an electron and a positron with particular energy, which of course is nonsense. Probabilities are between 0 and 1. So there's no possible way that the theoretical characterization of the observables here can possibly match the experimentally determined values. I'm fine. Thank you. So this is the first kind of obstacle to the interpretation of the theory, the first kind of problem with the exactness, or the first kind of violation of the exactness requirement. The diagrams with closed loops are ultraviolet divergent. This problem, which was discovered already in the late 1920s, was the subject of much concern for several decades, and made people wonder whether the theory could be used meaningfully at all. But in the late 1940s, we have from Dyson, Feynman, Tominaga, and Schwinger a result that created some reason for hope, which was that they showed that a finite set of redefinitions of the parameters in the theory suffice to render every individual order of perturbation theory finite. Here's the trick that they used. Rather than letting the momentum in this internal loop get arbitrarily large, what they say is, let's just integrate up to some large finite value lambda. Then the integral looks like the log of lambda, which is finite for any finite value of this ultraviolet regulator lambda, because the log of lambda goes like the plot shown there. And if you use this trick to determine the finite set of redefinitions of the parameters, what you see for the electron-positron scattering that we've been discussing is that the sum of the first 3 terms of the perturbation series actually matches the empirical data very well. You get exactly, or you get a theoretical prediction that's empirically adequate. It gets the data correct. But this procedure, at least at the stage at which it was available in the late 1940s, has some kind of associated conceptual problems that make you wonder whether the procedure is in fact conceptually well defined. And in particular, one of the things you need to note is that imposing this cutoff lambda induces a minimum distance in the space-time. And this breaks the symmetry of Minkowski space, and we thought, after all, that we're creating a relativistic theory, so this seems like a problem. And this is one of the ways in which the techniques of perturbative field theory run up against the requirements of axiomatic field theory, because exact Minkowski symmetry is strictly required in axiomatic field theory. In fact, it's one of the axioms on some characterizations. But beyond that, it seems like we're just making an ad hoc modification to the theory designed simply to get the right answers. And this attitude, and Laura illustrated kind of nicely how the reaction that quite a number of people had to this kind of process, this kind of way of regulating the ultraviolet infinities. But fortunately, in 1970, in the late 1960s and early 1970s, Ken Wilson comes along and shows that there is in fact a principled and physically well-motivated rationale behind the renormalization procedure. And the idea that comes from this work is that the empirically adequate field theories are supposed to be construed as effective field theories. The idea of an effective field theory is just that the measurable low momentum empirical content is insensitive to the high momentum dynamics that we ignore when we impose this ultraviolet regulator. And moreover, the renormalization group shows us how the structure of the theory changes as the cutoff is removed. So something you can do once you have the technology of the renormalization group that Wilson developed is you can look at the value of the theoretical observable that we calculated with the regularized theory, and you can see how the value of that observable changes as the regulator is taken back to infinity, as you restore the exact symmetries of Minkowski space. And what you find when you do that analysis is that the values of the theoretical calculations for the observables do in fact change. You get some movement in their values, but they only move up to a finite level of accuracy. So you can place a principled bound on how much that empirical content is going to change, and that's this epsilon theory, this theoretical error. Okay, so this renormalization group analysis shows that the relevant empirical content is insensitive to the high momentum regime in this sense. And in fact, a number of philosophers, the renormalization group realists that Laura was discussing yesterday, have advocated that in order to bring interpretation to bear on the world, we in fact need an effective field theory interpretation. David Wallace, in particular, has gone so far as to argue that axiomatic field theory can't be empirically adequate precisely because it requires an exact treatment of arbitrarily short distances. And recall that the claims I'm advocating are as follows. So the ultraviolet, infrared, and large order divergences can all be overcome by letting empirical content have finite precision. So the renormalization group analysis shows us that the claim one is true of the ultraviolet divergences. By studying how the behavior of the theory changes as we remove the cutoff, we get this finite precision, and this overcomes the ultraviolet divergences. And you might think already now we have a conclusive argument for claim 2, that to interpret the empirically adequate models, we need to abandon the exactness requirement, which is precisely just what Wallace says is true in virtue of the presence of the ultraviolet divergences. But I don't think the argument for claim 2 is in fact so straightforward. There's an escape route for somebody who wants to defend the exactness requirement in this case. And in particular, the escape route is that if we attend to the mathematical details of what produces the ultraviolet divergences, what we're led to is a way to characterize the theory that avoids them entirely, in which no ultraviolet divergences arise. So something that I've argued is that, in fact, if you produce this analysis, then what you find is that empirically adequate quantum field theories can be cast in a way where these ultraviolet divergences don't arise at all, And moreover, you can take this solution to the ultraviolet problem for perturbative field theory and directly incorporate it into axiomatic treatments of the theory. So what that shows is that the ultraviolet divergences themselves don't provide conclusive grounds that we need to abandon the exactness requirement, as Wallace says. So if we want an argument for claim 2, we're going to have to look elsewhere, and a natural place to look will be to look to the next class of divergences, which in this case are the infrared or long distance divergences with the theory. So before I get into that, let me just point out where we are. So we've started calculating the S matrix, this thing that's going to tell us the probabilities for the outcomes of scattering experiments. What we saw is that when we do the calculation of the first few terms, if we're lucky, we first get a finite term, but then each subsequent term is infinite because of the ultraviolet divergences. But through the renormalization procedure and an effective field theory interpretation, we can remove the infinities from the very short distance contributions from the integrals. But the question we need to answer now is, are all of these terms that we get out from this process in fact finite? We've only checked that they're finite in one particular regime. We need to check the rest of the integration region. Okay. So the next problem results from the fact that photons are massless, and so it costs an arbitrarily small amount of energy to emit one with arbitrarily small momentum. So what this means is that in addition to the diagrams that we saw before, we're going to have new diagrams that are related to the previous diagrams by the emission of very low momentum photons from the outgoing final states. And we can radiate an arbitrarily large number of photons from any one of these final states with arbitrarily small momentum. So let's look at the simplest case of this kind of diagram and see what we get. So again, we have input, the lambda is still the ultraviolet regulator here, and the integral corresponding to this diagram goes like log of that ultraviolet cutoff over the photon mass. But of course, the photon mass is 0, and so once again, this is the log of infinity, which is once more infinity. So even though we've dealt with the ultraviolet problems from the very large momentum regime, when we look at the very low momentum regime in the theory, we get a new kind of infinity that crops up in the theory. And again, these are supposed to be probabilities, so our theoretical characterization of the observables is not giving us something that matches onto the world. So this is the second obstacle to the exactness requirement, and it's that the diagrams with the emission of low energy photons like this are infrared divergent. But now we have a strategy for coping with this kind of situation. We just need to cut off the infrared divergences just like we cut off the ultraviolet divergences. This can be done in a variety of ways. One of the ways that you can do it is by introducing a minimum momentum in the theory, just like we introduced the maximum momentum to cut off the ultraviolet divergences. And once more, what you can do once you've imposed this now infrared regulator is with that you can study how the predictions of the theory change in the limit as the cutoff is removed. In this case, in the limit as the very low momentum is restored to the theory. And what we see once more when we do this analysis is that the values of the observables do move as the cutoff is taken down to 0 in this case. But once more, it doesn't change that much. It's the amount that it can change is bounded by this finite level of theoretical error. It's not the same as the theoretical error in the ultraviolet case, but it is a principally determinable amount of theoretical error. So observables that are insensitive to the removal of the cutoff are called infrared safe. So I should note that not all observables have this property of having this stable amount of finite theoretical error in the infrared case, as they did in the UV case. So we need to restrict the class of observables to these infrared safe observables. But when we do that, we're also able to take the theoretical content and let it be defined up to this finite amount of theoretical error. Okay. Now, there's no currently available escape route to avoid this kind of theoretical error and maintain the exactness requirement as there was in the case of the ultraviolet, as I showed. But just because there's no currently available escape route doesn't mean that there isn't one. I don't have a principled argument that there couldn't be one. And so if we want an argument for claim 2, we're still going to have to look to the third class of divergences. That's where we'll get the argument for claim 2. But note that we've now checked off both the ultraviolet and infrared cases of claim 1. Okay. So let's finally turn to the large order divergences. And the question we need to face up to now is, now we do have an infinite collection of terms which we know all to be finite, but it's an infinite collection of finite terms, and we need to ask whether or not that infinite collection of finite terms actually sums up to some finite value. The answer, Dyson argued already in 1952, is that the answer to that question is no. In fact, if you add up all of that infinite collection of terms, you get a large order divergence. So once more, for the third time, when we try to calculate the values of the S matrix to generate predictions for scattering experiments, we get infinity out of the theory. So let me indicate what this particular kind of infinity means in practice. The anomalous magnetic moment of the electron is one of the celebrated empirical successes of quantum field theory, and it can be measured very, very precisely in a variety of different ways, and it can also be calculated to 5 orders of perturbation theory. And what you find when you compare the theoretically determined value of that observable to the experimental value is that they agree to more than 10 decimal places of accuracy. Feynman famously compared this level of accuracy, or actually an earlier version of this calculation, to theoretically determining the distance between New York and Los Angeles to the width of a human hair. So in those first 5 orders of perturbation theory, the theory seems to contain something really valuable empirical content for mapping onto the world. But what Dyson's argument shows us is that if we continue to add up the terms in the expansion, which is what the theory tells us to do, not only are we going to get the wrong answer, we're going to get infinity once more. So at this stage, you might say, okay, enough of this. We've kind of beat down all of these infinities that keep arising. No matter what we do, the theory keeps spitting back infinity at us. But I think, in fact, the resolution to this problem is also something that we can achieve if we think along the lines that I've been advocating. What I want to note is that this kind of large order divergence is something that's been noted in many other contexts besides quantum field theory. Abel was one of the first people to encounter them, and he says that divergent series are the invention of the devil, and it's shameful to base any demonstration on them whatsoever, but that most of these things, the truncations of divergent series at early orders, are correct. In spite of that, is extraordinarily surprising. I'm trying to find a reason for this. It's an exceedingly interesting question. Now, Abel died the next year, so he didn't have a chance to explore the question further, but in the subsequent years, mathematicians did find a clear explanation of how it can be that the early orders of a perturbative expansion can contain good empirical information, even if they go on to diverge when you sum them to all orders. And that explanation is that perturbation theory is asymptotic to some exact structure that's lying behind the success of the perturbative expansion. So asymptoticity is just a requirement that the exact value, the difference between the exact values of the function and the partial sums, the early partial sums, are appropriately small for every order of perturbation theory. So let me just show you how this gives you an explanation. Here's a nice function that we might try to represent with a series. And what we're going to do is compare 2 different expansions and how well the two different series represent the function. One is convergent, and one is asymptotic. So here's the convergent series. What's plotted is the differences between the exact value of the function and the nth partial sum of the perturbative of the expansion as a function of how many terms of the expansion are included. And what you see is that for about the first 10 orders of the expansion, we don't get anything like a good approximation to the value of the function. However, if we sum out to more terms in the series, say 30, for example, we get about 7 or 8 decimal places of accuracy. And because it's a convergent expansion, if we continue to include every term in the expansion, we of course know that we'll get the exactly correct answer in the limit where we include everything. The asymptotic expansion behaves differently. It shows us that at the very first order of perturbation theory, we already get an answer that has 6 or 7 decimal places of accuracy. That behavior continues for a few more terms, and then, of course, the expansion diverges. It's a divergent asymptotic expansion, and so eventually we start to not just get the wrong answer for the value of the function, but we get a divergence off to an infinitely wrong answer for the value of the function. But of course, this is precisely the behavior that we see in the expansion for the anomalous electromagnetic moment. So it's in this sense that the conjecture that perturbation theory is asymptotic to an exact structure is an explanation of the empirical success of the theory. Okay, so now you might wonder, well, does this criterion of asymptoticity tell us anything about the exact structure lying behind the success of the theory? And unfortunately, it turns out that many different functions can have the same asymptotic expansion, and so it doesn't tell us anything about the exact value. But there is a condition stronger than asymptoticity which determines the function uniquely. It's called strong asymptoticity, and it just requires that these differences are even smaller than we required when we imposed asymptoticity. So a strong asymptotic series uniquely determines the function. If you know the strong asymptotic series of a function, there can only be that one function lying behind the success of the early terms in the series. And if you know the strong asymptotic series, the function can be uniquely reconstructed from the series by Borel summation. So the idea of Borel summation is to divide the coefficients in the expansion by n factorial and integrate to recover the exact function. And what I've argued is that in those cases where a model of axiomatic quantum field theory is available, the models of axiomatic field theory that we have, the perturbative treatment of the theory exactly and uniquely determines that model through this process of Borel summation. They really share a common structure for these models. So now you might think, okay, we're making progress, but can we define the Borel sum of the empirically adequate models? And to answer that question, we need to look not at these early diagrams in the expansion that we've been considering, but out to the large orders of perturbation theory. And what we see when we look there is that there's two new problematic classes of diagrams. One are a collection of graphs called instantons. There's n factorial such graphs, each of which make a small contribution at each fixed order of perturbation theory, but for n large, n factorial of even a small contribution is a big contribution. And then renormalons, which are just individual graphs that make a contribution like n factorial, which of course for n large is going to be large. And what the presence of these graphs means at large order is that the division by n factorial in the Borel transform is insufficient to completely tame the large order divergent behavior. N factorial divided by n factorial is on the order of 1, and if you add up 1 an infinite number of times, you're still going to get infinity. Okay, so what this means is that, in fact, there's no unique exact solution lying behind the empirical success of the truncated expansion. But you can put a positive spin on that situation And note that the truncated expansion that we use to get empirical information about the world still does bear a well-defined relation to the relevant class of exact solutions. And by optimally truncating the series, which is something I can explain later if people are interested, we accrue this final ineliminable theoretical error. We can't get rid of it because we have a principled demonstration that there's not one exact structure line behind the success of the theory. So what that means is that large order divergences leave us with no option but to abandon the exactness requirement. So what we've found is that as we calculate the S matrix, we encounter these three different classes of divergences, but the methodologies of practicing particle physicists allow us to get out, at the end of the day, if one's willing to go through all of these steps, a characterization of the theoretical content of the observables up to some finite level of theoretical error. So that completes the arguments for claim 1 and for claim 2. We've checked claim 1 for each of the three cases, and in the case of the large order divergences, there's no way to remove the theoretical error that we accrue. And let me just briefly indicate where I think that leaves us. So we've been considering this exactness requirement, which says that it must be possible to determine the empirical content of a theory exactly, at least in principle. Here's a forceful kind of characterization of this requirement from Rivasot, who says that any formal power series being asymptotic to infinitely many smooth functions, perturbative field theory alone does not give any well-defined mathematical recipe to compute to arbitrary accuracy any physical number. So in a deep sense, it is no theory at all. This is just a statement of the exactness requirement. What I've been advocating is that while Rivasot is of course correct that we don't get arbitrary accuracy in the characterization of the observables, what we do get is a characterization of the observables that's defined up to some small, relatively small theoretical error. And another line that I've pursued is to try to understand whether or not defining the content of the theory up to that level of error is actually sufficient to get out something that can in fact be construed as a legitimate physical theory. And I think you can. And I think you can do so by just taking empirical adequacy to be established when the theoretical characterization of the observables with this theoretical error attached to it is compatible with the measured, or the experimentally measured values of the observables within the measurement error. Okay. So if one's willing to take that as a criterion for empirical adequacy, then what you can show is that the exactness of empirical content that we've kind of found in quantum field theory can in fact be rigorously incorporated into the semantics of physical theories. There's no reason not to think that quantum field theory is in fact, the empirically adequate models are in fact physical theories. And I think that this provides an understanding of the sense in which quantum field theory is in fact a theory, as I just said. And what was required to kind of generate that understanding is noting that each of these obstacles that we encountered to interpreting the theory is in fact a hint about how quantum field theory holds its empirical content. So if one adopts this perspective, the project of interpretation, the project of trying to understand what the theory is telling us about what's there in the world can proceed, using in the context of the empirically adequate models, but with the understanding that the characterization of the empirical content of the theory that it gives us is not defined to arbitrary precision. It's only defined up to some finite theoretical error. And I just wanted to note, before I leave off, that I do think this has consequences for many of the different topics that have been debated in the foundations of quantum field theory and the philosophical investigation of quantum field theory. But I don't think it's limited to just that context. I think, in part, many different approaches to quantum gravity are defined, at least in some respect, as having to recover the reliable empirical content of quantum field theory. And in light of that fact, I think it might be of some interest to people trying to develop or understand the consequences of quantum gravity, philosophical consequences of quantum gravity, to know what, in fact, the reliable empirical content of quantum field theory that needs to be required actually is. And that's what I think I'm trying to get to in this kind of collection of. Thank you very much.
So let's just say I buy your argument entirely. So one thing you suggested is that we need to adjust for us into notion of empirical adequacy, which was it that within the models of the theory there is one that fits the empirical substructures to the observable data, something like that. So you said that instead so that's a sort of modified or like a partial isomorphism claim. And you said, well, we just need to compare numbers basically, and if the theoretical error is within the experimental error, then it's empirically adequate. I'm just wondering where that leaves us as a starting point for an interpretive project, as in asking what the theory says about the world. I mean, is one then committed to some sort of empiricism or operationalism where all your theory is a tool for getting the right numbers within those bounds, or is there some hope for the traditional philosophical predictive interpretation?
Yeah, good. So I think that this pulls in the direction of something like operationalism or instrumentalism, or various varieties of empiricists kind of commitments, is the natural inclination that people have. And I'm interested to kind of try and understand in a better way how people are, what aspects of what I'm saying are pulling people in that direction. But I guess one thing I would say is that there's nothing about this that's by necessity going to have an empiricist reading. All I'm trying to do at this stage is to provide what I think the reliable empirical content of the theory is, the kinds of things that we actually measure, the kinds of things that we can actually take from the theory and compare to experimental values, and that's something that anyone is going to have to do if they think that what they're talking about is to show that the theory is in fact empirically adequate. But yeah, so then the project of how do you actually go about interpreting the theory, I think can at least start along similar lines. But I do think I have sympathies with some of the kinds of claims that get made in the literature that Laura was discussing yesterday about, and I think the results here, to my mind, are just kind of contribute further evidence to those kinds of claims that what we need to do if we want to interpret the theory is to really establish in which situations the theory leaves us some kind of robust or stable structures, relatively long distance structures, relatively low energy structures that we think are reliably there in the world. I think the result of this can lead to very similar not just a similar picture, a picture that kind of contributes further evidence to that kind of picture of how the interpretive project should go.
Maybe another way of asking that question is, say I come to the axiomatic formulations that you discussed, and take that as my interpretive basis, which that's going to be somewhat operational. Reactions generally get some sort of operational interpretation, but I take that to be the basis of my realist interpretation. It seems to me that the considerations you've presented do push in the direction of saying, well, maybe we shouldn't take interpretations of models of those axioms that seriously. Do you think that's a wrong, is that not an implication I should be drawing?
I don't think you should take the interpretations of the axioms seriously if what you mean by that is that you think that amongst the models of the axioms, what you're going to find is a model that says something about the actual world. But because the models of the axioms that we have that are available contain idealizations that we know don't match on to the world. So the failure, what I tried to show is that the failure of the models that we, of the empirically adequate models to satisfy the axioms is actually much more mild than people have kind of presumed. So I think when Siegel says that what we have, the models that we have that actually generate empirical adequacy are a collection of partially heuristic technical developments, that's in fact much too pessimistic. There's actually very well-defined connections between the empirically adequate models that we have and axiomatic models. And so the axiomatic kind of treatment does provide kind of an important basis for the beginning of the project, the interpretation. But if what you mean by using the axiomatic formalism as a foundation for the interpretive project is just that you're going to try and take a model of that and map it onto the world, it's not going to work. Now, that's not to say that somebody can't modify the axioms in some way, according to which you'll be able to show that the empirically adequate models are exact with respect to those new axioms. That's in fact something that I think is a completely open question. But then what one wants to know is why does this project work of using the perturbative models as we have them? Why does that allow us to match on to the world? And all I'm trying to do is kind of push that line as far as it can get.
Could I get out just one more quick follow-up?
Yeah, I think so.
So are you leaving open the possibility that whatever it is these series are asymptotic to could be a model of some of the axioms we have? We just don't know it yet, or
it won't be a model of axioms that we have,
okay.
But there could be generalizations of the axioms, and I don't know. I don't want to make the conjecture, but I think it's certainly open that there's a mild generalization of the existing axioms that the perturbative data that we use to match onto the world could be exact with respect to. Yeah.
Thanks.
Chris, do you have a question?
Yes, I do. Yes.
Well, ask it.
Can you switch off the... Okay, thank you. So the exactness requirement says that it must be possible to determine the empirical content of a theory exactly. Now, do you reject that? And you seem to have said that this may be supported from theories of quantum gravity, where you have some sort of underlying granularity of the fundamental space, or if I got that point right. But if that's what the support for your thesis is supposed to be, coming from quantum gravity, I don't quite think it's the rejection of the exactness requirement that's really being warranted, because in a sense, if those fundamental theories turn out to be the right ones, then what we have is not an inexactness or a limitation of exactness. In a sense, the empirical content can be fully, exactly, precisely determined. It's just that there's a certain feature of that fundamental reality that we can, in principle, exactly empirically see that is such that the fundamental structures are discrete or granular or something of that kind. And I'm not sure whether that will solve the problem, but if that's right, then perhaps it's not exactness that we have to give up, but something slightly different.
Yeah. So that's interesting. So I guess I wasn't trying to suggest that the kind of various approaches to quantum gravity that we have, especially those with a built-in granularity of some sort.
There,
Sorry,
if you want to
sorry.
actually look
I'm
at
trying to look. Okay, sorry. Yeah. So I don't think that's a reason to abandon the exactness requirement. I think the idea is that what we know the project of quantum gravity has to do, or one thing it has to do, is in the end, it has to recover the empirical successes of something like the standard model. And what I'm trying to do is give a characterization of what we should expect that recovery, what has to be recovered for that project to be succeeded at. But maybe I should go back and kind of give some more motivation for this requirement. So I'm not subscribed to the requirement, so maybe I can't motivate it as well as someone who is. But I think it's in fact supposed to be a logically weaker version of something that is adopted if you require that what it is to be a model of a theory is just to have a structure that exactly satisfies the axiomatic kind of syntax of the axioms of the theory. And that's, I think, it's just a nice kind of thing that captures what goes on in a bunch of standard approaches. So, yeah. But if I don't know, there's a few different lines here, and I'm not sure which of them you're most interested in hearing about. But I think the thing. Sorry.
Sorry, thank you very much. That's helpful. So the idea then is that it's not the empirical content of the fundamental theories of quantum gravity that we don't get exact, but those might give us justification for taking the empirical content of the quantum field theory not exactly.
Yeah, that's right.
Idea?
That's right. Yeah, so I'm perfectly well open to the idea that there's some new theory beyond quantum field theory, string theory, loop quantum gravity, causal set theory. Pick your favorite quantum gravity approach to quantum gravity. I'm perfectly open to the idea that there's some new fundamental theory waiting for us at scales which currently are not experimentally accessible to us. The only point about quantum gravity I'm trying to press is that all of these approaches, in some respect, are characterized in terms of having to recover the standard model at the end of the day, because we know that that's what the relatively long distance physics of the world actually is. But then the question is, well, what does it mean to recover quantum field theory? And that question is has been thought, at least in some circles, to be rather difficult because we don't have an exact mathematical characterization of what a quantum field theory is, or not for the empirically adequate models. All I'm advocating is that this is kind of one way to think about what an empirically adequate quantum field theory is as mathematical object that's well defined, well describable, and which can serve as kind of the target for the recovery. Yeah.
We have to follow up. Just one thing. Maybe you could extend your argument to quantum gravity theories or approaches which use the same kind of QFT tools you are looking at.
Yeah.
So maybe you could extend your argument to the quantum gravity regime as well.
Asymptotic stuff.
Yeah, or just different approaches which use this kind of expansions and.
Yeah, so certainly in the case of string theory, you resolve some of the ultraviolet problems of the theory. Similarly, I think for loop quantum gravity, I'm less familiar with causal set theory. But in the case of string theory, which is the one I'm at least mildly familiar with, the large order divergence difficulties that are present in the case of quantum field theory are also present in the perturbative characterization of string theory that we have. In fact, the large order divergence difficulties are even worse, at least as so we understand from some simplified models. It's a question that hasn't been explored as well. It's been explored in quantum field theory. But yeah, so I think at the end of the day, this inexactness might in fact percolate down even to a perturbative characterization of string theory, for example, but that's something where I just don't know enough of the details to advocate at this stage.
Even in loop quantum gravity models or spin phone models, they use the same kind of QFT tools, and maybe you could just make the same kind of argument there. I don't know.
Yeah. I think it's entirely, it's not unlikely. I think, so one thing I'm also interested in is to what extent these kind of large order divergence difficulties are generic in treating problems perturbatively. They happen in all kinds of, they come up in all kinds of contexts as simple as n-body Newtonian gravitating systems, perturbation theory for non-relativistic quantum mechanics. So there's nothing special, at least, there's nothing particularly special about the quantum field theory case with respect to the large order divergences, except that it seems to be the first instance that I'm aware of where this failure of Borel summability arises due to the presence of these instantons and renormalons. But in string theory, it seems like you're going to get analogous large order effects that are going to also create that non-Borel summability at least. And perhaps in other quantum gravity situations.
Thanks.
Can I ask, is it a follow-up, or do you want to? Can I ask a follow-up, which I thought was part of what Chris was asking, but then went in another direction. So thinking about the quantum gravity cases, I think lots of that gets said lots of the time is that there's no space-time below the Planck length or something like that. So I'm just wondering. So this is probing not the sort of philosophical position so much, but trying to understand exactly what better what the exactness requirement is.
Yeah.
So exactness in that case can't mean sort of giving predictions or to arbitrary accuracy at all. I mean, if the prediction was, say, one about lengths in that case, you wouldn't be able to make a demand that quantum gravity gave a prediction that was exact, beyond the Planck length. I'm just kind of wondering. So the question is sort of, if you do have, it seems like the exactness is in a sense tied to the idea of a continuum space-time, and so it's not always going to be clear how to apply it.
Yeah. So that's an interesting thing to think about, is what happens when the spectrum of an observable is actually not just discrete, but it has discrete values as the possible values. And there, then I don't think you will have a problem. But presumably, you're going to want to calculate observables in something where you have, even if you have a finite length built into the theory, you're going to want to calculate observables other than lengths, presumably. But you'd expect the theory to say something not just about lengths, but about energies.
Right.
And so if the observable...
Here's the sort of idea. When you're thinking about this requirement of exactitude on the observables, what you've suggested to me suggests to me. I mean, there's two kinds of observables, right? One's that actually are recognized as fundamental within the theory, and those better get exact values. But there's others that are going to not be recognized as sort of fundamental. They're going to be derived or sort of emergent or something, right? I mean, so like thermodynamic quantities with respect to statistical mechanics.
Okay.
But I don't see why the derived ones should be expected to get exact values just because they're derived. I mean, we now have a sort of theory about what those observables sort of how they relate to more fundamental stuff. And that relation may be one where they just don't get exact values according to the fundamental theory.
Yeah. So I'm not sure I know what you mean by fundamental. So is a cross-section a fundamental or a derived observable of quantum field theory?
So this isn't really a question about the application of this to quantum field theory, but just trying to get the idea of exactness. The cross-section, like the scattering amplitudes, they seem to be sort of fundamental in quantum field theory. I guess that's right.
Yeah. So
in a quantum case, it would, whatever you'd set up the quantum system, and it would just have whatever Hermitian operators there were, they'd be the observables. That's fine.
Yeah.
But you might introduce but when you're actually thinking about matching it up with the empirical world, there might be quantities that didn't naturally correspond strictly to observables, but were sort of coarse grainings of observables, or kind of averages of observables, or something more complicated. And there it just seems that relationship could introduce sort of irreducible ambiguity in the values.
Yeah. Yeah, I guess I'd need to get a better grasp on how one reads off what the fundamental observables are supposed to be. But it seems like even in
so the quantum gravity case was supposed to be like the quantum gravity case. So,
but there's surely
the classical theories we're trying to recover seem to give you make sense of observables, sort of distances to any sort of scale. But that's given the way the imagined way one would understand what a distance is according to a quantum gravity theory.
Right. Okay.
One would think that wasn't fully meaningful.
I see. And the thought is that might extend not just to distances, but to all of the observables using quantum field theory.
Insofar as they're spatio-temporal in some way, yeah.
That would be an interesting scenario, but I need to understand better how you make that kind of correspondence.
Yeah. I guess that's the project.
I see.
Yeah. Okay. Laura.
Oh, yeah. Okay. So, I guess this is a question about why make some choices about what's vague rather than others.
Yeah.
But I'll have a prologue. and like the prologue is, once we've noticed that theories are effective, this kind of mechanical way of going about understanding them starts to seem wrong-headed. And the mechanical way of going about understanding them is taking them to be true, figuring out what the world has to be like in order for them to be true, and invoking that picture of the world to explain why they succeed as far as they can, as much as they do. And maybe even basing your account of their empirical content on that sort of interpretation. But once we recognize they're effective or take seriously the possibility that they're effective, the explanation of why they succeed as well as they do is going to be the truth of some other theory. The higher energy theories. But once you have that idea, it seems natural to acknowledge that nearby to any effective theory, there's going to be a bunch of other effective theories that are neighbors in virtue of saying very similar things about the phenomena as your favorite effective theory. Okay, that's the prolegomena. The question is, would you want to talk me out of this way of thinking about the material you presented? So a quantum field theory, there's a question about how to individuate it. And one way to go is, specify a Lagrangian and take its theoretical content to be vague along the lines you've described. Another way is to say the Lagrangian corresponds to a family of quantum field theories, and members of this family are individuated with respect to an ultraviolet cutoff, an infrared cutoff, and a truncation procedure. And each of those has an exact content, and that family is sort of a cluster of effective neighbors. And is there something, am I going to miss something about how quantum field theories, real quantum field theories take on empirical content if I think about things that way, rather than assigning each theories an exact, individuating theories differently and
Yeah.
assigning them an exact theoretical content.
Good. Yeah. So good. So I think at the end of the day, you can tell that there's a way of turning this on its head, which is, I think you're describing it a little differently than I would describe it, but where that's going to be the situation. So when you have this kind of underdetermination of what the exact structure lying behind the success of the data that we're using to match onto the world, one idea is that there could be a fact of the matter about which of the structures compatible with that low order perturbative data is successful, and that is going to correspond to one particular structure of the exact structure. The only reason I don't know that I can block that I don't think I can rule that kind of reading out. The reason I'm hesitant to assent to it wholeheartedly is that it doesn't match the way that we use exact structures to get to the empirical content that does match onto the world. So I think what I'm trying to do is just to kind of take the methodology, take the method that is in fact successful for getting to the empirical content that matches the world, and try to give the best story about what that allows us to kind of infer about what's lying behind the success. And what I see when I look at all of these methodologies is that there's nothing about having that one true exact structure that seems to be playing any role in getting to the success.
Right.
And so I can't say, I don't have an argument that there's one of the infinite class of things isn't the thing that's generating the success. But I do have an argument that nothing about having that one true thing seems to be at all relevant for getting, I shouldn't say at all, but for getting to the successful, the empirical content that matches the world. And in that sense, it's kind of, I think that, I find that, to me at least, that's a compelling reason to think that that level of exact structure specification doesn't really matter for it.
It doesn't help us understand why the theory succeeds any better. Yeah, no, I agree with that. I guess a kind of tangential question.
Sure.
It's what you think the world is like. Like in these cases where the non-Borel summable asymptotic series matter, there's going to be a bunch of functions they approximate. And I don't think this necessarily matters one way or another to your account, but I'm wondering what in your heart you feel about questions like this. So is it the case that it's simply sort of indeterminate ontologically which function is there, or is an equivalence class of functions a single kind of ontological thing, or is in fact one of them is sort of the physical referent? You could reject this whole question by rejecting this kind of talk, but this is sort of back to Tom's question about what the difference is between empirical meaning and physical meaning. Is the physical referent one of them, and as a practical matter, it makes no difference to us which one it is, because as far as the empirical content goes, it's
so good. So on independent grounds, I'm doubtful about the project of kind of taking the mathematical structure of the theory, reifying it, and kind of creating this image from which the physical kind of world is going to be generated or something like that. I think that that's kind of too simple of an idea about how the structure is connected to the meaning, not for the reasons I've discussed here. I think to do that requires it's a complicated project. As you, I think, have forcefully and importantly emphasized, we get a theory. The mathematical structure of a theory never arrives to us just in a mathematics textbook. It's partially interpreted. We have kind of already associated with it ideas about where the physical meaning is supposed to get attached to the various gadgets that are involved in the theory, and so on and so forth. So I think there are aspects of the mathematical structure which do underwrite stable kind of things that one can actually be ontologically committed to, like the in and out states, free states of the fields, corresponding particles. I think there's something like that's you have warrant for thinking that there are electrons, things like that come out of experiments. Whether that story can be continued to the real like interaction region of the fields, that's not so clear. I'm not aware of a way to do that. So one thing I think I'd say is that I don't think we should have a flat ontological commitment to the same kind of ontological commitment to all the different aspects of the ways you want to attach physical stuff to all the different mathematical aspects of the theory. But in terms of how the results I've discussed here is connected to this, I'd say there's two kind of pictures you might come away with. So I've said I believe that there are electrons, but what we're saying is that some facts about electrons, like their magnetic moment, might not have exactly determined values to all to arbitrary accuracy. So there's a couple of things you might think about that. One is that there just is in fact no physical fact of the matter about what those additional digits of that observable are. I think that's one natural reading of what's going on in our representation of them. Or you might think that there is some fact of the matter about it, but quantum field theory doesn't deliver it to us. And the point I'm pressing is that both of those situations are perfectly compatible with everything we've ever done or seen about electrons. And I don't think I have grounds to kind of support one or another of those things. But I do think it's important to note that the exactness requirement that I think is lying in the background of some people's kind of thoughts about what it is to have a respectable scientific theory is really a profoundly strong requirement. It's saying that for any observable in the theory that can take on continuous value, that, there has to be a physical fact of the matter about the 10 to the 5,000th, or I can keep going, value of observables like the electromagnetic moment. I don't know why one would be committed to that on kind of empiric grounds. There's nothing about our investigation of the world that's indicated to us that that's the situation that those are. I'm not. If it turns out at the end of the day that those kinds of observables have a finite level of accuracy, I suppose I'm just not that.
But doesn't that? Sorry.
Go down. Go for it.
I mean, that to me just seems like such an obviously fallacious thing to think. I mean, like Newtonian gravity presumably is, on that sort of model, you might say, well, it demands every planet has an exact mass.
Yeah.
But that just seems, I mean, not just because of like GR or something, but it just seems like that's sort of enough, not going to be a reasonable assumption that given what planets actually are made of, that it's not going to have an exact mass. So
because of Tibbles-like reasons, because it's going to be up for grabs exactly what the extent of the planet
I think
is.
all kinds of reasons. Yeah, I mean, because you think it's composed of other stuff, and that might
what
not
point
have
do you
a
cut off the atmosphere and things like that?
Yeah, but maybe the GR as well. You think that might be a better theory, and where that's not going to be such a reasonable question. That was like a gravity on the mind from your talk. But other kinds of properties we think that things have. Generally, one thinks anything. I don't know. I think high-level properties aren't defined to arbitrary accuracy just because they are sort of higher level properties. But that is, I actually
will
thought
say that you're
the
first person who shares this
Okay.
intuition.
Okay.
that
I mean, I
I've
thought there was
encountered.
another kind of motivation is
Yeah.
that if you haven't, which was like the quotation I found towards the end, look, if you haven't given a model where everything is completely logically crystalline and pure, you haven't really given a theory, a story at all.
Yeah.
So that would be a different kind of demand for exactitude, that there was some, yeah, you hadn't sort of specified a theory unless you'd specified it exactly.
Yeah. Yeah.
But that seems wrong to, I guess that seems wrong to me as well, but yeah.
In a deep sense, it's no theory.
In a deep sense, it's not there at all. So this is something that I'm actively trying to get more information, like trying to get more people. Many people have this intuition that if you don't say what all the facts of the matter are about all the observables, then you haven't given like what we properly mean by scientific theory or a physical theory, and that's just a. I just would like to get more of an idea from people where that intuition is coming from, because when I try to evaluate what the mass of what is my height at a given instant, for example, I think it's a hard question to actually answer if you want to answer it not to 2 decimal places of accuracy, but instead to 2010 or go on forever. And I start to think about those kind of considerations. Where's really the top of my head? Like, am I really flat? Or am I really organized vertically? And so on and so forth. And so I'm just not disturbed at the end of the day. Those things come out as kind of not having an exact fact of them out of that.
Yeah, I mean, things like height, it seems, if you change the degree, if you start asking for more accuracy, you have to be more specific about what height actually means. You're actually going to change the meaning of what height is in most cases. Right. And maybe for any level of accuracy, you can give some specification so that there are.
Right. So I think that's the picture. I think that should be the picture about the anomalous electron moment too. I think for the purposes of quantum field theory, we have an understanding of what that means, but maybe it will turn out that what we mean by that, that the meaning of that term, that theoretical term, is going to change in a similar way in the context of whatever the new theory is, and then maybe more accuracy can be attributed to the value.
But I didn't take that quote to be making this point about we've just been discussing about whether actual electrons have a exact, well-defined magnetic moment, but rather just a condition on what, a sort of a logical kind of condition or sort of semantic condition on what it is to actually be a theory, that it has to be exact. Well, but that seems equally problematic because most physical theories in sort of history aren't exact in that way,
Well, but so
many
I think
that aren't sort of axiomatizable in that way. So lots of things we take to be knowledge aren't knowledge at all if one has that condition.
No, but so this is, I think, this is an expression of the tension that's present in the literature about quantum field theory. That this is something that people are committed to. That in order to have a proper, if you look at what Halverson's saying when he says to have, in the absence of a mathematically intelligible quantum field theory, he's saying in the absence of a theory that satisfies this requirement. I think that.
Right, but so I agree with that. But so what I'm saying, they might still be able to. He might be able to accept. Yeah, look. I mean, actual electrons. There is no kind of the magnetic moment isn't a well-defined quantity to arbitrary degrees of arbitrary sort of decimal places. But I still want this criteria. I still want exactitude, not because I think it reflects something about the world, but because of what it is to present a piece of knowledge to somebody.
To be a model of the theory. Yeah.
Yeah.
If you're committed to the idea that what a model is a structure that exactly satisfies the syntax of the theory, then this, I think, you're committed to.
Yeah, I mean, and indeed that the theory is such that it always entails exact numbers. I mean, one could imagine a theory where it was just because of the formulation of the theory that everything came with inexactitude.
I might have seen a finger in Geneva.
Okay.
Oh yeah.
Geneva, do you have a finger?
There's even a text. Yes.
I'm not sure I understand the metaphysical conclusion that you draw. Because at the beginning, I thought that what you said was that a physical theory doesn't need to make a prediction to what a physical quantity is to any degree of accuracy. So the claim was scientific theory can just give you a range, and they do not need to make a prediction, an exact prediction of a precise value or approximating to a point. But then you seem to draw a metaphysical conclusion that, in fact, there is no fact of the matter. So the physical quantities are somewhat ontologically fuzzy, and I don't see what the step is. It seems that you could say that there is some value. Was this? I don't remember what the example was, but a given physical quantity, but you could just permit that there are scientific theories which simply do not pronounce themselves. They just give you an interval.
Yeah, no, so I agree. I haven't tried to argue that you have to give this the interpretation in terms of metaphysical indeterminacy or something like that. I'm just saying that, and what Nick and I have been discussing is that if that turns out to be the situation with the world, it's not, it doesn't contradict anything about kind of our experience with the world so far. But yes, the option that it might turn out that the world is such that there is a fact of the matter about the exact value of the observable, but the theory doesn't reveal that fact of the matter to us, is a completely open option that I haven't given an argument for. I think those are both completely viable alternatives at this stage.
Are there more questions in here? Sorry. I think I kind of wanted to... You've sort of answered this a couple of times, maybe in the talk and in response to Tom. So this is really just to help me out, and really to help. So given the story that you have, which is sort of defending the meaningfulness of the sort of observable quantities in the face of the problem of exactness, maybe it's what a number of people have asked. Anyway, that starts to sound that there's just going to be a sort of empiricist interpretation of the theory. Is that right? Or so you sort of saved the observables, but given the worries about anything sort of, or the lack of knowledge of anything more fundamental.
Yeah. So the best understanding I have of this at this stage is that what I've tried to do is to take the kind of practice that we have with quantum field theory of calculating observables, taking the apparatus of the theory to calculate observables, and compare them to experiments and get the right answer. Okay. So as I was telling Laura, I don't think you can just then say, okay, we get the right answer about the observables, so we should say that mathematical structure kind of maps on the world or something like that. I think the procedure for trying to generate ontological conclusions on that basis is more intricate, and in particular, what you need to try to do is to try to give an account of, given the fact that that practice is successful in matching onto the world, what inference about what's there in the world is warranted by the nature of the success that we generate. And I think there are some genuine ontological commitments that can be made, like that free electrons are things that the theory represents faithfully in terms of the mathematics of the three states is something that actually does kind of correspond to something there in the world. But then the question of, can this be extended to all of the mathematical structure of the theory? I don't quite see an argument for it. I think I don't want to flat just because we get the right answer for a cross section doesn't mean that we have an exact kind of quantic picture of what's going on internal to the interaction of the fields with each other.
Yeah, I mean, given the insensitivity to more fundamental, that seems like a really good case to be worried about the underdetermination. Yeah. I mean, one thing I think, one talks about observables in quantum field, quantum mechanics, I mean, sort of Hermitian operators, as like something like that. But that doesn't track sort of realism and empiricism. I mean, there's lots of observables that don't correspond to anything you can see with the naked eye or anything like that, or even that are sort of indirect, can be measured as easily as a cross section.
Right.
So observable sort of just means physical quantity in general. So are you sort of happy? I mean, does the same kind of does the reasoning that you've presented, right, give us an understanding of what all those physical quantities are, whether they're observable or not in the sort of empiricist sense?
I don't know.
Maybe that's too broad a question.
So grand is that? But, yeah. I think all I can really say is that I think the project of generating what the ontological conclusions from success ought to be is something that you can't do just from the mathematical structure itself, the input that we get from doing it there.
Anybody else here? Do you have any more questions at that end? They froze. Hold on. They're just looking really intently.
No, I don't think so.
I had a sort of comment rather than a question. I mean, I think the example of the electron is a good one because it sort of seems like, we say in, I don't know, 1900, we might have expected it to be a point particle with a definite mass. And then when we got quantum mechanics, we might have expected it to have a definite mass and a definite charge, and the gyromagnetic moment is going to be exactly 2. But we learned that those are sort of bad questions to ask about electrons. They're constantly interacting through QED. So, we did learn in a sense that those aren't sort of exact quantities. What is the? Do we really believe that there's a meaning to the bare charge of an electron? Is that something that we think is metaphysically meaningful? I mean, it seems like you could say that we've actually learned through the course of 20th century physics that there are some quantities which seem to be perfectly determinate, that given what we know now, perhaps are not so determinate.
That's exactly my attitude.